Hi there, we continue to learn how to build JavaScript Chip-8 emulator. And right now we're in VS Code and we're gonna check the real code, and I'm gonna explain how does it work. And so you already seen this demo, like with the 6 numbers on the screen, and also this tag that we use, this HTML, Vanilla JS, and Tailwind for styling. Also, you have seen in the previous videos how architecture of the system is organized. So it's basically some model of CPU, memory, input device, output device, and right now we use just 3 of them: memory, CPU, and output device as a display. You see this black screen here, so it's an emulation of the display. Memory is presented as an array in JavaScript. And also instruction set, this is quite simple, 3 groups of them: data manipulation, flow control, and display. This is all we need to decode in order to work with the display and to change something on it. Let's take a look. Everything is put here in index.html. It's by the way, you can check GitHub, where you have all the source code available. And so here's basically classical HTML page. What is interesting, so here we add Tailwind CSS, so it's just hosted version. I don't really use built version here just for the sake of simplicity, so it's just loaded from this URL, and then I use Tailwind CSS styles. So I style body with the utility classes, and also the main thing is here. All the emulators, just all the elements is here. And what is interesting here, whereas like the key part I would say of this emulator, is this canvas tag. So this is exactly where we draw that works as a display. Just a quick recap: that canvas, this tag allows you to draw anything you want using JavaScript, so it's a quite powerful tool in order to display something for graph and many other things. And the only thing you should know that we just use ID of Chip-8 display in order to refer that element in DOM, so there we can perform some operation with that. And so we're getting back to the script itself. So everything is organized in class Chip-8, so we can just right now just toggle it just to see the whole structure of the app. Now then we go deeper in the Chip-8 itself. So pretty much what we do, this is the step-by-step explanation. So we start from canvas. So as we have this Chip-8 display ID, so we use classical DOM getElementById function, and so we get the canvas. Then we use this canvas as a parameter to the constructor of this Chip-8 class, and so after that we have Chip-8 object of the class Chip-8 that we can use in order to work there. I've created a simple function getX. This is just helping to position these numbers on the screen, and it's basically uses offset and use 5 pixels with the standard shift for every position, so it just can help us to move the elements on the on the screen. And so we have simple program. So here comes a bit to a tricky part, I would say, for the guys who never worked with some kind of a low-level programming. And so also maybe not many of you know that JavaScript supports also hexadecimal version of the numbers. And so here it is. So here you can feel yourself real hackers, because here it's like 0x represents something that is in a hexadecimal then. And so every command here in this simple program is represented by a hexadecimal number. And I've organized that in rows that pretty much start with a standard start. So we set y coordinate, and then we perform this x coordinates and drawing of the specific number, and then we just loop back, pretty much jumping back to the beginning of the program. So as we discussed in our architecture video, this is the program itself. It's
It's a set of instruction. In our case, it is an array. It's the data structure of JavaScript. It is an array. And every operation has 2 bytes code, and here it is represented by 2 numbers. So it's 2 bytes represent just one operation of Chip-8 virtual machine. And so here we have one operation, and here we have, as you can see, this one. This is the first one using this helper function. This is the second, and this is the third. And you see they are the same here, and here they are the same first part, and it's just different the second. And here also the first part is everywhere. It's a 0, and we have only this number changing. And what is happening here? So pretty much we use this data manipulation command, 6.1, in order to set the y coordinate, 6.0 command to set x coordinate, and we use this command, and this is the value that we want to save. And we use helper function in order to calculate the offset position that we want to store. And then the second is function that sets the address of the sprite that we want to draw, and in our case we want to draw numbers, and numbers are stored in this Chip-8 memory starting from the address of 50. And whenever we talk about hexadecimals, we don't rename it's 50, we just say 50 to be sure that it's not mixed up with the decimal system, because it's not actually 50, it's like 5 times 16 plus 0. And so we increment this in order to refer to the different numbers. And so it's like, you see, it's just added 5 is added here, so we move step by step for the next digit. And the last command is the same. It's pretty much to draw D0. It's command that draws on the screen something of the length of 5, and which is the case for our symbols. And whenever we have the program, it is some array of these opcodes, operation codes. We just use a load program method, and we just invoke it like using this program, and it's loaded to this Chip-8 emulator memory. For the sake of simplicity, I console log what we have in the beginning. So PC is it is the counter of commands where pretty much that CPU uses in order to see at which instruction it is right now. And whenever we move, like, it's pretty much incremented. Like whenever we, like, the standard flow is like whenever we move forward, just like to the next operation, we just incremented by 2, because every operation it has length of 2 bytes. But whenever we have this change control flow instructions, they can jump to some arbitrary places, and in this case this program counter would be changed to this value. And so this then we have this run function, nice run function, that is invoked at the end, and this run function is can use this speed variable, so in order to cycle this, so we invoke a cycle, then we render display, request animation frame, and that's it. And we just pretty much repeat, because in request animation frame we just run the same function, so it just starts over and over again. And just for the sake also for debugging and just to see in the console log what's happening, we show what is in the program counter for the moment. And this gives you an idea of what it is inside the program organization. And also very interesting part is the Chip-8 class itself, because here's like all the details of Chip-8 virtual machine is encapsulated, because whenever we don't see it, it's pretty much it can be any kind of CPU inside. For any kind of CPU we just can have some reference to canvas, to some display. We're gonna have some program that is some set of instructions. We can load the program to this system and then just run it. But all the magic happens inside. And in our case, this is this particular implementation. And this goes straight to as in specification of Chip-8 system. So we create array of 4 kilobytes of that unsigned integers, and so we use it as a variable memory. So V stands for 16 registers, so we have number 16. So we have this index register that is initialized as 0. Then we have program counter that starts from 200 200. That is the address where we load our program. Stack is empty, and stack is emulated here by array. Stack pointer is set to 0. Delay timer and sound timer are initialized by zeros. Display, it's pretty much array that we fill with 0, so it's like it should be empty at the beginning. So the size of the array is 64 by 32. So here we have it like kind of explicitly. Also keys, it's not used right now, but 16 keys that can be used, and the status of pressed, not pressed is like initialized as false. Whether the machine is paused or not is, so definitely in the beginning it's not paused, so it's false. And speed is like 1 instruction per frame. Whenever we want to speed it up, we can change this number, increase it, and in this case we're gonna have for 1 frame we're gonna have more cycles and more instructions. This is the font set. This is pretty much what we use in our program in order to draw these symbols, and it starts from 0 and goes up to the F symbol. And this is hexadecimal representation, so it's every element is a byte, so it's 8 bits that zeros and ones, that ones represent something to show, so it's a pixel that can be set to white, and if the screen is black, because otherwise it's going to be a bit different operation. And also we have 5, so it means we have 5 lines, so 5 rows, and every row has 8 columns. And so if we have number F, so it means that pretty much we would have the first nibble, it's called, the first 4 bits would be just they're gonna be just ones. So this gives us an idea of the symbols and what is happening here. So we load them to the memory, and the starting address is 050. So this is where we put our symbols. Then we set up the canvas. So remember, we get this from constructor's parameter. So it's the argument of the function, of the constructor function that we use here. And so then we do classical JavaScript work with the context. So we just call this canvas get context. Then we have context, some fill style. It is blue, but anyway, we redefine it in, like whenever we draw something. We set the width and height, so we scale every pixel by 10, so in order to see this on the screen, because otherwise it's going to be too small. So we have the scale here, and the scale factor is 10. I think I'm going to update that to use the constant in order to modify this scale factor easily. So the next go load program method with the details, and so what we have here is just quite straightforward. So we have also, as we loaded font set, we have this program, and we just load everything from the program array to the memory array, starting at the address 200. So it's basically we rewrite everything that was there. We just like update it with the new values from the program itself. And also there is a console message saying, hey, we have this program loaded. Cycle, this is pretty much one of the crucial part of this machine. So this is where all the work is done. So remember, like in this run function, we call this cycle function. What happens here? So first of all, we fetch opcode. So we use these shifts, and what we want to have here is just to create the 2 bytes opcode that we can execute then. So we use this current location, we use this next location, and so in this case, next location gonna be the lower part of the value, and the current location is gonna be the higher. So we shift it to the left, so basically we multiply it. So it moves left, then with the OR, we just by bitwise, or we just say that on the right is going to be the value of the next byte, and on the left is going to be multiplied the current value. Then we have this 2 bytes opcode, and we execute it, and just update timers, and if nothing goes wrong, we just increment the program counter. And so then goes the classical switch statement, where we decode our operation code and perform some actual operations. So we have also some console log just to see where we are, and also here's we implement the standard decoding of Chip-8 opcodes. So we use masks in order to, you see like here with the F, which means for ones, we just try to get the X value that is pretty much positioned in this 4 digits. So there's going to be a 3rd digit that we try to track. Here's the 2nd digit that we try to track. KK is just the last 2, and here's like 3 of them. So the mask that gives us an idea of what is the last 3 numbers. And here's just the last one. Depending on the operation, they use different sorts of that, but we calculated all of them just for the sake of simplicity. So whatever we need them, we just already have them. But for some operations, anyway, we don't use all of them at the same time. So it's going to be either X, Y, or for instance, NNN. It's not used together. So then we just have symbol operation. Also, we just try to track the first symbol, because it encodes the operation itself. And if it starts from 0, we check for clear display. If it is clear display, so we just have this array display that we just fill with zeros again. If it is return from subroutine, we just get the latest value from stack and just load it back to the program counter. So whenever we need to jump to some address, we just explicitly set the program counter to this address, and yeah, that's it. And so we get back, and after this we can call a subroutine. This is where we save before. When we call something, we just save this program counter in stack, so we can get back if needed with a pop operation. So we just push it there, replace program counter with the value. So this is the param that we already calculated. This is part of the opcode. Yeah, and here we are. We just get it back and skip instruction. So if register with the index X equals to KK from the operation, just skip it. Setting, so it's data manipulation stuff. So we pretty much just assign some register with index X. We assign this KK value that is part of the opcode itself. If we need to add something, we pretty much do it and try not to overflow. So in this case, we just trying to be sure that it's not greater than 1 byte, so it's not greater than 255. Setting I to 3 ends is just quite straightforward, so we just assign it. And the cool thing about the drawing sprite is just it's a bit more elaborate. So here we have Vx, Vy. There's the addresses that we use location to locate the pixel to draw. So they're stored like in Vx, Vy, and in our program we really do that. So we set the universal Y because they are all placed in the same row, but we increment Vx by 5 in order to move forward with a new letter. So height is n. In our case, height is I think it was 5, yes, for 5 pixels. And also no collision, we don't use it right now. And so height, we just have a loop. So pretty much we have a loop, and inside this loop we trying to get the sprite. So we using memory and address is I index register plus current row that we use. And so for then we have this sprite, and all the sprites are 8-bit. So in this case we just really know that we just need to draw all the 8 columns here, and we just calculate the pixel itself, so whether it's 0 or 1, and we try to find index inside the display. So we just, what we do, we try to find the index. So we calculate the row and col, and not trying to overflow. And I mean, in the case of the overflow, we just we're gonna show this up on the other side, because it's like we use modulo operator, and we divide it by 32. And so we calculate the index inside display. In this case, we check whether it is at this address. If we have 0 and pixel, if it is 1, it means that we have pixel is 1, and we already had 1. In this case, it's going to be collision, and it tries to do an XOR operation with this pixel. So whenever we had something, we just would see the opposite value. If it was 1, it's gonna become 0, and if it was 0, so it was black, it would become white. It becomes 1, and that's it. Just repeat it 5 times for the height, and then 8 times for 8 columns in order to draw it. Yeah, and the last one is the render display. So this is pretty much in this function, in like whenever we call this operation, we update memory. So in memory we would have new representation of the screen, but the screen doesn't really know that we updated it. We need just to redraw everything we have in kind of a video memory and translate it to the real pixels we see on the screen. And this is done here just with like flushing all the stuff that we had, just removing everything that we had before with a clear rect. So we just remove everything, and then we just fill everything with white, saying whenever it's like gonna be filled, we just gonna use white color. And yeah, that's pretty much it. That we check whether like the specific pixel of the display we have 1. So in this case we fill small rect using pixel size as a kind of a dimensions, and so we draw this small pixel on the screen, and this gives us the whole idea of how all this stuff works. And whenever we run this program, we're gonna see this
these 5 numbers, and we're gonna see them over and over again. I hope that this was useful. You can like, subscribe and share, and follow to learn more and to build up your JavaScript skills in order to progress with your career and earn much more. See you guys. Bye.